Okay, we started recording. Let's wait a few seconds.
You want to be extremely punctual?
No, but what if someone just joined late or something? It may happen.
Oops. My screen sometimes goes to sleep, but hopefully not when I write. Now it's, oh yeah, why do you put everything in GMT? Nobody really knows what GMT is. I had to Google what time.
I'm British. I have to do something British. Yeah, so it's like,
But that's BMT. It's not even I mean, it's not even 3 now in the UK.
Yeah, but this is actually the best of GMT. So it's like a British, but not even British time. Yeah, historically. So no,
Exactly.
I don't know. It sounds good, and it's neutral. It's like everyone in the same position. Yeah, including UK. Oh, Piotr Pakora.
Okay.
Yeah. So,
if you want to show your face, that would be very nice. I would greatly appreciate it because I see like a little window with everyone's face and it's nice to know people are following. But if you prefer really not to, then you don't have to. Hello.
Okay, let's start. So it's my big pleasure to introduce Liana Heuberger from University of Angers, and she will speak about how to construct new Q-Fano threefolds using Laurent inversion.
Thank you for the invitation. And thank you for being here to all of the audience. I know it's like past the halfway mark for this marathon. So like everybody who actually went to see things saw all of the things pretty tired, I guess. So I really appreciate this. Okay. So this is joint work with Tom Coates, Al Kaspczyk, and Giuseppe Piton. And even if the title doesn't really say so, it's going to end up being a mirror symmetry talk. But we are not going to start like that. We're going to, use your empathy powers and assume you are me, and then assume you have the following thing. So, oops, see, already like assume all you know about a Fano threefold, say X, is its anti-canonical ring. Okay, how do you construct this variety X? I guess that's the question I want us to think about in the beginning. Okay, well, the most basic thing that you will think about when you start looking at this problem is to use embeddings. So the easiest embedding is the one via the multiple of the anti-canonical linear system that is very ample. So we've already seen this. So find a multiple of minus kx that is very ample and embed x into some projective space, Pn. Okay, everybody's familiar with this from like what we learned in the beginning of Introduction to Algebraic Geometry. Okay, you embed x into this Pn, but I mean, it depends now what you, what find or construct means for you. So once you do this, you may notice that the codimension, so the embedding codimension here is too high in order for you to write equations down for x. Because you have structure theorems for these kinds of rings, the coordinate ring of x, which would be Gorenstein rings, and you know how to write these for certain codimensions, but if it's too high, you have no control on these equations. Okay, you try to do a bit better. The second type of embedding, in which you use the graded ring structure of the anticanonical ring, right? Because I said you know all of it. So use the entire anticanonical ring. To embed, very similarly, into a weighted projective space. which I will denote just P, and then you'll have some weights, let's say until 8K. And this will lower your codimension necessarily, but sometimes not enough. And unless you can divide -kx further in the class group, then you're pretty much stuck with what you can do. However, you can, make a list of all these people, of what possible anti-canonical embeddings are for a given Fano variety with, let's say, that admits terminal singularity, so not too bad. And indeed, there is such a thing. It's called graded ring database, short GRDB, which contains about 55,000 of these conjectural, I put this in inverted commas because whatever, varieties. So you start with all possible Hilbert series, you build the embedding space, this is an entry in your database, but you never know whether these varieties actually exist. And the thing is that when embedding codimension is strictly larger than 5, so when I say embedding, I mean embedding with the whole canonical ring, so the optimized version, these varieties are virtually impossible to construct.
Excuse me, may I ask a stupid question?
Yeah.
What is this entire anti-canonical ring?
Well, oh, sorry. I mean, every person in these, just any kind of, let's say, M multiples of kx. You know how many sections and who they are here for any M positive, obviously. So you know all of the anti-plurigenera. Okay?
You mean in the first you took just some powers? I didn't understand. What's the difference between the first and the second?
So in the first, you just use a fixed multiple of -k. In the second, you use all of the previous multiples of -k smaller than the M you find in the first one. And if you use the fact that the generators are independent, you will end up shortening the list of, shortening this capital N to something a bit smaller. Something like that. Okay, I can tell you about it like later on, but this is quite straightforward. All you need to know is like Riemann-Roch for surfaces, for threefolds. Okay, so you cannot really reach these, and it's very hard to reach them by rational constructions, or if they have like a special structure, like their conic bundles over things or whatever. If you only have the Hilbert series, it's very difficult to just determine them. Okay, so my talk, so the main result of this talk is that I can construct, I'm not claiming all of them, but I can construct such varieties up to codimension 19, I think is the highest. And I'm going to underline the fact that for many years, it was thought that anything higher than codimension 5 doesn't even exist. And sort of the entries in the database are empty, but they're not. Okay. Let's start. So how do we do this? Well, we use the mirror symmetry approach to classifying Fano varieties. Okay. So I'm going to use a version of mirror symmetry for Fano varieties, which I find to be the simplest one for what I need to do later. Of course, there's a lot of discussions into what precisely the statement is. So I'm going to say that mirror symmetry in the case of Fano is the one-to-one correspondence between, let's say, X n-dimensional Q-Fano. So this means I'm also, well, that is terminal. These guys modulo deformation, so up to deformation, correspond bijectively to certain, So you've probably seen this in Alessio's talk. If you follow Zag religiously, there has been a talk about what certain actually means 3 weeks ago. So I won't really discuss this. So certain Laurent polynomials in n variables up to mutation. I mean, I won't discuss what mutation is either. I will just take a Laurent polynomial and it will help me find the Q-Fano variety. But let's not get ahead of ourselves. So this is sort of the mirror symmetry statement that I am interested in. Let's say that I take a Laurent polynomial here, f. I'm going to rephrase this in a more geometric way. So by taking the Newton polytope associated to this polynomial f, I will call this guy P. So this is a polytope that lives in a lattice of dimension n. So the dimension, the amount of variables that f has. I can build a toric variety xp. And again, if you've heard a lot of Q-Fano mirror symmetry talks, you know that toric geometry is instrumental in whatever you want to prove in this. So the more geometric version of the statement that I said before is that this one-to-one correspondence is actually reflected in a deformation, which I will say, so I will say here Q Gorenstein, but
So
this is just
Q-Fano means Q Gorenstein.
No, Q-Fano means a Fano variety whose anticanonic, well, okay, a multiple of the anticanonical is Cartier.
Yeah, it does mean Q Gorenstein.
No, it doesn't mean Q Gorenstein. No. The deformation is Q Gorenstein. That's, okay, something I will say, deformation. To the Q-Fano X that we want to see. So there is more geometric meaning in the sense that these Laurent polynomials don't just fall from the sky. You can sort of get a hint of what they should be by degenerating your variety X onto a toric variety XP. Q-Gorenstein deformation for me essentially just means that minus MK is constant in this deformation family. So how many sections I have in minus k, in minus 2k, etc. for x is the same as how many sections I have in these things for xp. And also the degrees are the same, so kx to the n, etc. Okay, so what else did I want to say? Yeah, so basically working around this degeneration or smoothing, so this is the degeneration, this is the smoothing, has been at the epicenter of this sort of research here. Maybe I would like to say a bit about going from X to XP. So most of my talk will be concentrated on going from XP to X, but now I want to speak about what has been done going from X to XP. So this part of the correspondence. So going from X to XP has been studied and essentially solved if X is a complete intersection in a toric variety. So there is literally an algorithm for how to do this if X is a complete intersection in a toric variety and it spits out a Laurent polynomial. An example for this, very easy example, is let's say you have a hypersurface of degree 6 inside of P1123. So P1123 is a threefold, therefore X will be a surface. And I'm just going to shamelessly throw out what the Laurent polynomial mirror to this is. So this is mirror to this guy F, which is just X plus Y plus 1 to the 6 over X squared times Y cubed. So if I had more time, I would tell you exactly how to do this, but I don't have a lot of time, so I will not. However, I would like to point out that this guy kind of encodes everything that is happening here on the left-hand side, because here I have the 6, which is the degree of my surface. And here I somehow have the sort of relevant weights in the ambient space. So somehow the polynomial brings together details of the embedding. Something else I would like to say is that, well, I said this has to be a complete intersection in a toric variety, and weighted projective space is just a Picard rank 1 toric variety. But if the Picard rank of the ambient space is a bit higher, then the Laurent polynomial that I will obtain will have more terms here. And now, if we think of what I wrote here about the Newton polytope and going to the toric variety, let's try to think of what the Newton polytope for this polynomial is. Well, it's just x plus 1, y plus 1, which is just a basic simplex, right? This is x, this is y, and this is, well, 0, 0 with a constant term, right? Now, if you want to put it to the 6, then you just enhance this polytope here, 6-fold. So you make something with the side 6. And then this guy here, if you want to just, when you divide by x squared times y cubed, you just basically take this basic simplex and move it around somewhere in your lattice. You just make a translation. So whatever you do, from the shape this thing has here, from what it looks like, you're just going to obtain a basic triangle somewhere in your space. The second term that would appear here, if you were embedded in higher codimension, would be yet another thing that kind of looks basic. I'm telling you this because now you and I are going to reverse engineer this process, because I told you my goal is to find Q-Fano varieties. So I would like to find x starting from an xp. And so what I would like to do is to take a Laurent polynomial, divide it into summands that kind of look like what I just did here. That kind of looks like a big mess, but whatever, this f guy. So I'd like to divide it into summands that kind of look like this, and then try to build the complete intersection inside of the toric variety thing. Okay, so this is like the basic idea. So, okay, let me write a bit and do a bit less blah blah. So goal, reverse engineer this. Okay, how? So using, as the title says, what is called Laurent inversion. So Laurent inversion is something that appears in a paper of Coates, Kaspczyk, and Prince, but independently, and I think a little bit earlier even. Kind of the same method has been done in a paper by Doran and Harder. However, what I'm going to present today will have sort of the language in this article, because these people are in my group and I'm more familiar with how they talk about things. And the basic thing is, so the motto here, oops, is to embed XP, the guy that we have, into a larger, by this I mean larger dimensional, toric variety, and smooth it inside there. Let's say this toric variety is Y, and smooth it there as much as you can, as possible, to get X. So we are reverse engineering this because for us, it's much easier to start from this polytope / Laurent polynomial business, because we have algorithms to put Laurent polynomials on polytopes. And also we have databases full of polytopes. So maybe it's a good idea for us to try to do this. Okay. So let's try to outline how this works. Okay, so setup for Laurent inversion. I will do this along with an example, so hopefully you can sort of follow what I'm doing. So the setup is the following. So as we said, we're starting on this side, so this right-hand side here. For the basic example that we're trying to do, I'm going to just use surfaces, and I'm going to even forget, at least for a little bit, that a Laurent polynomial exists, and just start from a toric variety. So that is a polytope, or a polygon, because we're doing surfaces, in a lattice N. The lattice is going to be isomorphic to Z2, a Fano polygon. By which I mean that by doing the face fan of the polygon, I will obtain a Fano variety. So the Fano variety will be XP given by its face fan. And then I will again do a piece of notation. So M is morphism, the dual lattice from N of N, also called the character lattice of XP. So this M and N are things you're quite used to if you do a little bit of toric geometry. So, okay, for this intents and for all intents and purposes here, I will do this polygon. This is P for me. It lives in N. Oops. I can do its face fan, so I connect the origin of the lattice with all of its vertices. I get a complete fan. I can build a toric variety starting from this complete fan by gluing together all sorts of affine pieces. You don't need to know this if you're not familiar with it. But here we go. So this is part of the beginning setup. Second part of the setup is I need an auxiliary object, which I will call Z, which is a smooth toric variety. So another variety. Ooh, not a smoother, it's just smooth. Toric variety whose character lattice is N. So whose fan lives in M, the dual lattice of N. There's going to be quite a little bit of shifting between left and right, M and N. So I'm hoping you guys are a bit comfortable with what is left and what is right. Otherwise, I hope you don't have a driver's license. But yeah, so let's pick Z for this particular P. So I'll pick one of the easiest varieties there are. I'm going to start by drawing its fan, because this is what I want. So I'm going to name also, because I'm going to need this later, the rays of its fan by row 1, row 2, and row 3. This fan of Z lives in M. I'm just going to say this is Z. Okay, and who is Z that has this fan? Well, Z, sorry, not isomorphic. It's really just P2. This is the fan for P2. Okay, so now I need to write a definition given these two guys. So a scaffolding. So the scaffolding will be S for scaffolding of P with shape Z is a collection of torus invariant divisors on Z such that, so I'll denote S as DI. These are the torus invariant divisors. It's going to be a finite collection, whatever, such that the convex hull of the polytopes associated to the DI, I in I, is equal to P. So before I can give an example, I have to choose a scaffolding of this guy. So in our example, maybe not with red, it's a bit of a mouthful, this definition, so I'd rather we look at something concrete. In our example, we choose, let's choose 2 of the di. So let's choose d1 equal c1 plus c2, d2 equal just c3. So c1, c2, and c3 are torus invariant divisors on Z, which each correspond to each ray. So if you know a bit of toric geometry again, each ray of the fan corresponds to torus invariant divisor on the respective variety. This guy is in O of 2. This guy is in O of 1. So these are 2 divisors. Every divisor that is like this, every Neff divisor, inter alia they are Neff, has an associated polytope that lives in the dual lattice. So it's also called the moment polytope. Maybe you've seen it. If you haven't, I'm just going to tell you that in particular, the moment polytope for D2 lives in N, which is the dual lattice, the lattice of the fan of Z. This is PD2. And you can see it is in O of 1 because it has size 1. It's a basic simplex of size 1. And this is great drawing skills. This is PD1, okay? The polytope associated to that one. And you can actually check that this is the scaffolding. Right now, if you do the convex hull of these 2 polytopes that I drew inside of the polytope P, indeed, the convex hull fills all of P up. Okay. So why are we doing this? Because it seems like it falls from the sky, like, you know, best idea ever, but sure. Why? Whoa. Why is it a good idea to consider this auxiliary shape Z, first of all? Well, okay. Let's see what the ray map of Z is. So this is just a map going from, oh, before I start this, denote R for rays as the number of rays in the fan of Z. So in our case, row 1, row 2, and row 3, small r is 3. So the ray map of Z is Z to the R goes into M. So the place where the fan of Z lives, and this is just 1, 0, 0, 1, minus 1, minus 1, right? Because these are exactly row 1, row 2, and row 3. If you look in my drawing, they're precisely those. Okay, so this is the ray map. Usually when you want to build Z as a GIT quotient, this is a part of a short exact sequence who we usually dualize. And so you get Z to the R dual, whatever that is. Every arrow changes direction. You get the dual of M, which is N. And then you get that N injects into this other lattice, which is of larger dimension. Okay, so now if you want to tensor with C star, you get, well, N tensor with C star is for us C star to the 2 is indeed the torus associated to the lattice N, which is the dense torus that lives inside of XP, which is the variety we care about. So this dense torus injects into C star to the R, again, whoever this is. And again, I wrote this is for Z, but I don't really care about Z. Z is an auxiliary object that I have. I care about XP. And my goal, as you remember from, you know, here, is to embed XP into a larger toric variety Y. By choosing this auxiliary object Z, I have managed to embed Tn, which is the dense torus. So this compactifies to XP. So I've managed to embed this dense torus into a larger dimensional torus. So my goal now is just to compactify this C star to the R in order to get a larger toric variety. The one that I wanted to begin with. Okay, is this clear? Does anyone have any questions so far? No? Yes? People love toric geometry. Okay. So.
Very clear, very clear.
Oh, you have seen this talk at least twice, Vanya. You don't count. Okay.
It was Ernesto.
Hmm?
It was Ernesto's comment, not mine.
Oh, really? Oh, thank you. Okay. Right. So now the theorem, of course, I'm not going to find the compactification because these people already have found the compactification. So the theorem is as follows. So given a scaffolding S of P, there exists an embedding of XP into Y. Y is a toric variety. Y is the toric variety that contains C star to the R as its maximal torus. But the theorem, okay, the theorem was Coates, Prince, no, Kasperczyk and Prince. The theorems, well, I mean, in their article, they also say more. They don't say just that the embedding exists, but they tell you what the rays of the toric variety Y are. So this with rays. Okay, so the rays are, again, Y. So the dense torus inside of Y is C star to the R. So the fan of Y will live in an R-dimensional lattice. So the first R rays are just the canonical basis of this lattice. So E star to the R, a standard basis of Z to the R. And then also minus DI. Why do I say minus DI? Minus DI also looks like it comes from nowhere. But again, you have done this for Z. It's again a basic fact in toric geometry, Cox chapter, I don't know what, that when you do this dual sequence here, the second one, what you will obtain here in the middle is nothing but, so I will rewrite it, so it's ZR dual there, is nothing but the torus invariant divisors on the variety you're writing the sequences for. So that's Z for us. And torus invariant with respect to Tm, which is the torus in M. Anyway, but you know that this group of divisors is actually generated by the divisors corresponding to the rays in the fan. So this is in fact generated by the Ci that we already know. So I equal 1 to R. Okay. So therefore, since the DIs are combinations of the CIs, they are also rays in this fan. Okay. So now that we have this, let's see what happens in the example that we kept working on so far. So in our example, what did we obtain? Yeah.
Is this Y unique? Sorry, it's Pedro. Or do you have some kind of freedom?
I think, so it's unique. It doesn't look unique with how I wrote it here, because of course for at least threefolds and higher dimensional things, you can, the rays of a fan do not determine the toric variety, right?
Right.
But a posteriori, and in the construction in the actual paper, it is unique. The thing is, you are building either a weight matrix or you are sort of tweaking Y so that you force XP to be Fano inside of Y somehow. Okay, maybe it will be apparent after I write like the threefold example. But anyway, so in our example, what are the rays of phi Y? So first of all, what's the dimension, sorry, not the phi y, of the fan of y, sigma of y. So what is the dimension of y in the example that we started with? So it's supposed to be R here, right? So y lives in the lattice Z of R. So the dimension of y is R. What was the dimension of y in the example that we had here? Well, the number of rays in Z, which is 1, 2, 3. So the dimension of y here in our example is 3. Therefore, here we are just giving rays in Z3. Okay, so that also why I chose to give a surface example and not a threefold, because you can actually still see things more or less. So, okay, let's start. So a standard basis, E1 to E3, okay? And then the amount, and then 2 more rays, one corresponding to D1 and the other one corresponding to D2, or minus D1 and minus D2. Okay, but now we have to look at who are D1 and D2. Well, we are here. The basis is C1, C2, and C3. And so when we put minus, D1 is C1 plus C2. So this is going to be minus C1 minus C2. And the other one is just going to be minus C3. Okay. So these are its rays. So now the question should be, what is the toric variety, the 3-dimensional toric variety, whose rays are the ones that you are seeing before you? And you can identify 2 really good looking blocks here. The first one looking extremely similar. I don't know, kind of like this one, for example. And the second one also looking quite similar. So actually there's a unique way of building a fan from these particular rays. And this tells you that Y is in fact, so P2, which is the first little box that I made there, times P1, which is the second little box that I made there, okay? You can always, if you see this kind of separation where you have zeros everywhere else except these 2 blocks, you can always be sure that the toric variety that you've obtained is actually just a product of 2 guys. Okay, so why is P2 cross P1? Now, something else I would like to say is that the theorem again tells you more. It tells you what the line bundle, so, okay, in this particular case, XP is going to be a complete intersection. And since you started with a surface, it's going to be, well, it's going to be like full on a hypersurface. So it's going to be given by just 1 line bundle. So, and XP is a section, and I'm going to tell you what it is, of O to 1 here. So what I've done in all of this stuff is to embed XP into P2 cross P1 as O of 2, 1. Okay, so XP is a singular person here, but you know that if you just write a general equation here in O to 1, it is going to be a deformation of your sort of singular toric variety in there. So general equation is, and it's smooth, F2, so a polynomial of degree 2, let's assume these are x's and these are y's, F2 x times y0 plus g2, second polynomial of degree 2 in x, times y1 equals 0. So this is the general equation, and you can check that it's smooth. So we've managed to put our toric element in there and smooth it out via this construction. Incidentally, you can actually tell which Del Pezzo surface you've obtained, right? Because you started with a Del Pezzo surface, which was singular, a toric Del Pezzo surface, which was singular. And through this construction, you've actually smoothed out the singularities it had, which were like 2.5, 1 points, I think. And you can see who this is by just looking at this equation, because again, the variables y and x are completely independent. And you can see that this is the equation of a blow up of the intersection of this guy and this guy in P2. And these are two conics in T2, which intersect along 4 points. So what we have obtained now is just this is DP5 by this construction. Okay, running out of time already. This is incredible. Okay. So, are there any questions at this point? No? Nothing? Are you smile if you're following? I don't know, something. Okay.
There's okay.
So,
No questions.
what? No questions? Oh,
Yeah.
sad. Okay. So even in this case, the codimension of embedding, so the codimension of embedding here is 1, right? Because it's a hypersurface, is lower than what I would have obtained had I embedded this variety with minus k, right? Like minus k here has a total of 6 sections in DP5. You can just do Riemann Roch surfaces. And it's already very ample, so I don't have to use the ring at all. So the anticanonical embedding of this would just embed it into P5, which is codimension 3 because it's a surface. So this already, so remark, this, so even doing this for surfaces decreased codimension from 3 to 1. For threefolds, which is what I work on, the situation is much more dramatic. So the descent of codimension is a lot more dramatic. But notice that what you had to do is to increase the Picard rank of the ambient space. So the Picard rank of Y here is larger. It's not a weighted projective space. So this is basically the concession that you have to make. So even here, the Laurent polynomial is somehow behind the construction. Because the pieces in which you decompose basically this polynomial, polytope, you decompose it into this plus this. Please don't take this as a Minkowski sum. This is not a Minkowski sum. Just a, you know, how to say, convex hull. Even when you decompose this into this, there was a Laurent polynomial here that always has binomial coefficients on edges. So it's always 1 to 1, 1 to 1 if the segment is of length 2. And kind of the same thing was respected by the pieces. So you did use a piece which had sort of coefficients attached to it, even if we pretended not to see the Laurent polynomial here. You could not have done something like, for example, use a polytope that looks like this, use a polytope that looks like this, and use a polytope that looks like this. Even if their convex hull does do the whole thing, the construction would not have worked. Or, I mean, mostly because this guy here would be 2 instead of 1. So you always have to have 1 at corners. Anyway, so choosing the factors here, the summands as a, like this, basically amounts to, you remember what we did in the very basic example where I said that if you increase Picard rank, then you increase number of summands. It's right in the first, these guys, this guy here. Well, it's precisely what we do, but in reverse. You have the F, which is basically amounting to this person, and you decompose it into 2 very basic factors that look like triangles. So this is exactly what we're doing here. Okay, so maybe I would like to say also that we have already used this method in order to find Q-Fano varieties using mirror symmetry, specifically for surfaces with a certain type of singularities, and even sometimes even to refine some of the smooth Q-Fano threefolds in the original Mori-Mukai classification. Okay, and looking towards threefolds, the deformation families are larger. So the case of threefolds is significantly more difficult. It's larger. The moduli space is even reducible sometimes. And so the goal is to find them in the largest possible codimension. as I said before. Okay, so now, it's your turn. So here is a Laurent polynomial that is sitting on top of a threefold polytope. And it is up to you to find the decomposition. Think of it as if it's a big inflated tent and you have to put sort of rocks in specific places of the tent that are specifically like heavy enough in order to hold the tent up. So in particular, you will have to put rocks at the edges of the tent. Okay, since we don't have a lot of time, I will help you cheat and I will tell you who Z is supposed to be. So cheat sheet. So Z here will be, well, a very familiar guy, P2 cross P1, only this time it's not going to be the ambient space, but it's going to be our auxiliary shape that helps us. If you think of, again, this decomposition here, you have to decorate the polytope in question with the moment polytope of the shape P2 cross P1. So I will also give you this so that you know what your building blocks are supposed to look like. So it's moment polytope is this guy. It looks like the product of the moment polytopes of P2 times the moment polytope of P1, which is just a segment, the product or the Minkowski sum, whatever you like to call it. So a triangular prism, basically. So I am also allowed, kind of like in the surface example, to expand as much as I want with certain constraints. So I can, I can dilate it. So initially, as I said, we have to take care of coefficients here, right? So this small guy here, everybody, all the segments involved are length 1. But I'm also allowed to dilate it. So make it a bit longer. And let's say that now this segment is of length 2. I should have gotten into drawing, guys, I mean, really. So let's say that this is 1, 2, 1, 1, 2, 1, 1, 2, and 1. So I'm allowed to dilate it, but I am also, oh my God, all of my drawings are, or contract it. So basically reversing this dilation until you get just one flat triangle. So I'm also allowed to use this guy, 1, 1, 1. Should have done it in orange, but who cares at this point? Okay, so with all this helpful information that I gave you, now you're supposed to figure out how to fill up all of that polytope so that you respect somehow all of the numbers that are inside it. Okay, any suggestions? Vanya, again, you've already seen this. Okay, so I will help you because again, I don't have a lot of time, so. First, we take this very long piece and we put it on top. And with this, I've taken care of all of these 1, 2, 1 guys here on top, okay? Now I'm going to take the same piece and put it on the floor of the house. And it fits right here. Okay, we are not exactly done. There is a person here that says 0, but in fact, that's a bit cheating because it's the origin of the lattice, and in the origin of the lattice, I'm allowed to put whatever I want because, well, two Laurent polynomials that differ by a constant term give the same mirror, basically. So as I hinted here, you're also allowed to use the flat triangle guy, and there's exactly one flat triangle that is missing for this picture to be complete, and it is this one over here, especially because this was a 3, right? So I only hit it with the 2 from the other shape. So basically, this is what a scaffolding of this polynomial is. And this is what I see every day, only like in a less pretty lattice. So, you know, just looking at polytopes with numbers on them. Okay, so once we have this, let me tell you what I obtain, and then I should finish soon. So I'm not going to write just the rays of y, because as I don't know exactly who, but somebody pointed out, it's not enough just to give the rays of a toric variety in order to completely determine it. So I will write the y that you obtain from doing this to xp, so this was xp, as a quotient of C, so a GIT quotient. Sometimes it's a lot more convenient to write toric varieties as GIT quotients. So by C star to the 3. Oh, by the way, y here, again, doing the same kind of calculations as before, is dimension 5. XP is dimension 3. So therefore, what I will obtain will be something that is a toric complete intersection of codimension 2. So I will intersect 2 line bundles to get XP on Y. So, okay, let's see what the weights of this C star to the cube action are. So 1, 0, 0. So there is an identity block here, which almost always happens. 1, 1, 0, 0, 0, 1, minus 3, 1, 1, 2, 1, 0, 2, minus 1, 0. So these are the action of a C star, each of them. And those are just the weights of the action on each of the 8 Cox coordinates on Y, okay? And then I also have to tell you what the line bundles that we have to intersect to get XP look like. And they have homogeneity type 2, 2, 0 and 1, 1, 1. So if you're not familiar with how this looks like, it's just a generalization of writing things in projective space or in weighted projective space, where you write what each of the weights of the action is. So this is very similar to just thinking of, oh, 2, 1 in some projective space, okay? And okay, maybe what I want to say again is that in general, Y, so Y is represented by this guy, so this is Y. We also have to say a stability condition. The stability condition is 1, 1, 1. Such a Y is very singular. It has an entire curve of non-Q factorial singularities. However, these line bundles also have a lot of sections in them, and they're very nice. And they manage to fully avoid the singular sort of non-Q factorial locus of Y. However, they do catch some singularities because we are not interested in finding smooth Fano threefolds. Those have been found a while ago in 81. I will find that an X, which is a smoothing of XP here, has these singularities. So they will all be cyclic quotient singularities because they are terminal. Whoop. So they will look like a quotient by a finite group. And these are the ones that I find. This particular example was something that initially was embedding codimension 13, and we have together created a codimension 2. Okay, I think this is what I wanted to say today. Thank you for listening. Sorry for going a bit overboard.
Thank you, Liana. Let's
You're
thank
welcome.
Liana with Zoom and with this. Thank you.
Thanks.
Any questions?
May I start?
Yeah.
Oh my God.
Okay. So thank you, Liana. So how many examples have you constructed?
This is what you always ask me. How many examples do you have?
Exactly. That's, you know, my question. Next time I will not ask. I will just open my camera and say, you know.
Be like, hello.
Yes.
I don't know. I found about, it depends on what you want. So for me, 2 people that have different mirrors are different. However, if you look in the database, maybe sometimes you just find 1 entry. So if you find that you just care about entries in the database, I found about, I don't know, 26, something like that. There are not that many because there are like 50,000 people in, you know, entries in general.
So 26 greater than code dimension 5.
Just to show that you can.
Oh, sorry.
Yeah,
so 26 which are in code dimension greater than 5. Or
I think they're all in code dimension larger than 11.
oh, okay.
They're
So
somewhere between 11 and 19. Anyway, yeah, if you think that okay, maybe it's kind of annoying to explain by hand waving, and I don't feel like turning on the tablet again. So you may go off into two different components of the deformation space of the same toric variety, right? Because these are sort of at the boundary. So I sometimes find that I can smooth the toric variety in two ways. And in this way, I would say that I found two different varieties. But for this, there is one entry. So if you count all of these that I found in this way, they're like, I don't know, 38, something like that. I never claim I can find like everyone. Obviously, that is a work that should require a computer by like clearly. But it's just quite surprising that you can map out how far, you know, how far this list actually covers geography that exists. Anyway.
So, but you cannot target specific one, but you can move with your method and then see, okay, where is this guy?
Mm-hmm.
That's what I think.
Okay, I think we don't have time for more questions. Yeah, let's thank Liana again, and you can ask her privately in chat. And let's clap here. Okay, thank you, Liana. Okay,
welcome.
Here. Yeah, good. And wait, I have to stop recording. Yeah.